And our company, Ares Ascent Corp, is committed to Mars. We aim to slash cargo costs significantly. Think a 70% reduction in launch expenses. This makes sustained human presence feasible. But it's not just about cheaper rockets. We must use what Mars offers. This is called In-Situ Resource Utilization, or ISRU. Relying solely on Earth for supplies is not sustainable. Imagine hauling every liter of water across millions of miles. The cost would be astronomical, even with cheaper launches. Therefore, finding and using Martian resources is paramount. It's the cornerstone of any long-term Mars plan. Without ISRU, Mars bases remain expensive outposts. With ISRU, they can become self-sufficient settlements. Water is the most critical resource we need. Humans cannot survive without it for long. Beyond drinking, water has other vital uses. It's essential for hygiene and sanitation. Water also enables broader activities on Mars. It can be used for growing food. Crucially, water can be split into hydrogen and oxygen. This means we could refuel spacecraft on Mars. Early astronomers once imagined canals on Mars. They thought they saw signs of intelligent life. These ideas were romantic, but ultimately incorrect. Modern science painted a different picture. Mars is cold, dry, and seemingly barren. Yet, the search for water continued. Subtle clues hinted that water wasn't entirely absent. These clues have grown stronger over decades of exploration. NASA's Phoenix lander provided direct proof in 2008. It touched down in Mars's northern polar region. Its robotic arm dug into the Martian soil. Just a few centimeters below the surface, it found something white. This material then sublimated. It vanished into the thin air. It was water ice. This was a landmark discovery. No longer theoretical, water ice was there. It confirmed that parts of Mars held accessible frozen water. Orbiters have also played a crucial role. The Mars Reconnaissance Orbiter, MRO, has been invaluable. Its instruments detected hydrated minerals on the surface. These are salts that have water molecules in their structure. Further studies revealed vast quantities of subsurface ice. This ice is a prime target for future human missions. Mars has a very thin atmosphere. Its atmospheric pressure is less than 1% of Earth's. This has profound implications for water. On Earth, water can exist as a liquid on the surface. Mars does not have this luxury. The low pressure creates a hostile environment for liquid water. It also makes exposed ice behave strangely. This strange behavior is called sublimation. Sublimation is when a solid turns directly into a gas. Think of dry ice on Earth. It's solid carbon dioxide. Water ice on Mars behaves similarly. If you expose a block of ice on the Martian surface, it won't melt into water first. It will slowly, or quickly, depending on temperature, turn into water vapor. This process makes surface ice unstable. Any ice exposed to the Martian atmosphere will eventually disappear. This is why the Phoenix lander saw its ice discovery vanish. It makes collecting and handling water ice tricky. If you dig up ice, you need to process it quickly, or you need to store it in a pressurized, temperature-controlled environment. Otherwise, your precious resource will literally float away. This presents a significant engineering challenge. BMAS. Mars has prominent polar ice caps. These are visible even with telescopes from Earth. They are vast reservoirs of frozen material. For a long time, we've known they contain water ice. The question is, how much and how accessible? These caps are not pure water ice, however. They have a complex composition that changes with seasons. This makes them a challenging but promising target. They represent a significant portion of Mars's known water. The Martian polar caps are made of two main ices. There's water ice, H2O ice, and there's carbon dioxide ice, CO2 ice, or dry ice. The seasonal caps, which grow and shrink, are mostly CO2 ice. Beneath this seasonal layer, especially at the North Pole, lies much more water ice. The northern residual cap is primarily water ice. The southern cap has a permanent layer of CO2 ice covering more water ice. We need to get to the water ice beneath. One interesting aspect is natural protection. The polar ice isn't always directly exposed. It's often covered by layers of Martian dust. This dust accumulates over eons. The prospect of liquid water beneath Mars's surface is tantalizing. While surface conditions make liquid water unstable, the subsurface is different. Deeper underground, pressures are higher. Temperatures might also be warmer. This could create environments where liquid water can exist. The search for this hidden water is ongoing. The MARSIS instrument on the Mars Express Orbiter is a key player. It uses ground-penetrating radar to probe beneath the surface. In 2018, data from MARSIS suggested a large body of liquid water. NASA's InSight lander had a different mission. It wasn't designed to find water directly. Its purpose was to study the Martian interior. InSight carried a seismometer to detect Marsquakes. It also had a heat flow probe, the MOLE. These instruments aim to understand Mars's crust, mantle, and core. Understanding the planet's structure helps us model where water might be. The seismometer successfully detected numerous Marsquakes. The Martian soil at InSight's location was unexpectedly stubborn. The MOLE couldn't dig deep enough to get accurate temperature readings. This was a setback, but the mission still provided crucial geological context. The search for accessible Martian water continues to drive exploration. It is a top priority for future human missions. Knowing where the water is and in what form is critical. This knowledge dictates landing site selection. It also influences mission architecture and technology development. Future missions will build on previous discoveries. They will employ more advanced instruments. The goal is to create detailed maps of Martian water resources. This will pave the way for human astronauts. Upcoming orbiters and rovers will carry sophisticated sensors. Some will have advanced radar to map subsurface ice in higher resolution. Others will carry spectrometers to identify water-bearing minerals. Rovers might be equipped with drills. These drills could sample ice from several meters deep. This is much deeper than Phoenix could reach. The Mars Ice Mapper mission concept is one such idea. It would use radar to find ice that astronauts could realistically access. Such missions are essential precursors. Alongside exploration, technology development is key. We need to develop and test water extraction systems. These systems must work reliably in the harsh Martian environment. Several concepts are being explored. One is called ROXY, Regolith and Ice Extractor for Mars. Solving the Martian water puzzle is fundamental. It's about the practicalities of human survival on another planet. Without local water, long-term human presence is impossible. Water is life, and it's also fuel and air. Its availability shapes our entire approach to colonizing Mars. The search for water is a search for our future on the red planet. Consider Venus, Earth's other planetary neighbor. Venus is a cautionary tale of planetary transformation. But today, Venus is a hellish inferno.